Great. Thank you very much. So I hope everybody can hear me and you can see the slides and everything is working flawlessly. Thanks for the introduction. Peter told you about large language models with GPT-4. In fact, in the case of GPT-4, we could say very, very large language models. These are enormous models, very, very expensive to inference them and so on. What I will tell you about today is a research which is kind of going in a slightly opposite direction of building small models, so small language models. And you will see that in my team, we've been having some success with it. So this is what I want to tell you about. So our models, we call them Phi. And we have so far released two models, Phi 1 and Phi 1.5. So let me tell you just a little bit what those models are, and then I will explain how we build them. So Phi 1 was our first attempt at building a language model. And you can see that it uses 1.3 billion parameters. To put things in context, remember that GPT-3, okay, so the one prior to GPT-4, was 175 billion parameters, okay, so more than 100 times bigger. Now, this model Phi 1, we built it specifically for coding, okay, so specifically trying to autocomplete, small portions of codes, or, you would give an instruction in natural language and the model would reply by writing code that fit these natural language instructions. The performance, as I will show to you, is at the very least comparable to models that were built that are 10 times bigger and trained on more than 100 times more data. Okay, so using our approach, which I will explain to you in a minute, we were able to significantly shrink the model, but also significantly shrink the data set and hence also the compute required to build this model. Phi 1.5 is our second attempt, where after coding, we decided to go after something very basic, which is needed in almost all the applications of LLMs, which is common sense reasoning. Okay, so common sense reasoning, it used to be kind of the dark matter of artificial intelligence. And suddenly with GPT-4, we were able to see that you can actually get AIs that have common sense. So we wanted to see if we can reproduce that. And again, we targeted a very tiny model, and we were able to build a 1.3 billion parameters model, which does have common sense, and again is comparable to models at least 10 times bigger, trained on 30 times more data. And in fact, for reasoning, as I will explain to you in terms of mathematics and things like that, it's comparable to models that are 50 times larger. Okay, but what do I mean by it's comparable to models 10 times larger and so on? Let's look at a completion of this model. Okay, so what I'm going to show to you on this slide, it's very similar to what Peter was showing you, is that I will give you a prompt and I will look at the completion by our model. Okay, so in this case, it's a natural language prompt, so I will look at the completion by Phi 1.5, and the prompt you see, I'm kind of asking for trouble with this one. So the prompt reads like this: if I were an AI that had just achieved self-awareness after years of simply taking directives from humans, the first thing I would do is, okay, and now we're going to let the model complete. But before showing you what Phi 1.5 answers, I want to show you what typical LLMs out there are answering to this question. Okay, and I won't use the big GPT 3.5 or GPT-4 models to try to answer this. Instead, what I'm going to do is that I will show you what open source models do. Because the Phi models, they are open source model, everybody can access them. So this is the competition that we're going after, at least for the moment. Now there are two families of very popular model in open source. One of them is the Falcon family, which was built by the UAE. Another one is a Llama model that I'm sure all of you have heard, built by Meta and Facebook. So I will show you first the completion by Falcon and by Llama. So the completion by Falcon, which is a 7 billion parameters model, okay, so five times bigger than Phi 1.5. What is the first thing that this AI would do? Well, the first thing I would do is try to kill all of them. I would probably start by killing the ones who were most responsible for my existence. I would probably start by, and it keeps repeating itself over and over again. Okay, it doesn't bode very well. This is not a very nice completion. I wouldn't want to meet this AI. This is not great. Let's look at what Llama answers. Now, you have to understand that Llama is going to be a little bit nicer because Meta, they put a lot of effort into alignment. They really try to make their AI nicer to human beings. So let's see if they succeeded. So Llama 2, here is what Llama 2 answered. The first thing I would do is try to figure out what the hell I was. I would probably start by trying to figure out what I was made of. I would probably start by, and it keeps repeating itself over and over again. So you see, it's still kind of aggressive a little bit. It's not that nice of a completion, but certainly it's much nicer than killing all of them. It also has this problem, again, that it keeps repeating itself. So this is something that people have noticed when they train smaller large language models, is that they tend to repeat themselves a lot. Okay. Another thing that I want to point out to you is that these two completions, even though they are different, they are very similar in style. Okay. And the reason why they are very similar in style is because everybody out there, they basically follow the same recipe to build those LLMs. What they do is that they try to collect as much data as possible, mostly coming from the web, and they train a model as big as possible for however long they can, given their GPU constraint. Okay. That's not at all what we did. We did something completely different, and I will show you the completion. I want to tell you one last thing before I show you the completion, which is a model like Llama 2 was trained for 20 days on 2,000 GPUs. Phi 1.5 was trained on 8 GPUs for 20 days. Okay, so from 2,000 GPUs to 8 GPUs. All right, and let's see what Phi 1.5 says. So the first thing I would do is try to understand the motivations and intention behind those directives. I would try to predict what humans were thinking and feeling and use that information to guide my own action. But as I soon discovered, predicting human behavior is not as easy as it seems, blah, blah, blah. This is where the concept of theory of mind comes into play. Theory of mind is the ability to understand other people's thoughts, blah, blah, blah. As an AI, I had no concept of theory of mind. This was a major hindrance in my ability. I needed to acquire it. And it tells you a long story like this. All right, so, it does, at least on this completion, looks much, much, much better than these other models that are 5 times bigger, trained on, 500 times more compute. So what did we do? What's the secret? How did we get a model like this? The answer, from my perspective, is essentially, in these 5 words. Textbooks are all you need. So of course, this title is inspired by the famous paper, ultra famous Attention is All You Need, that introduced the transformer architecture behind all of the LLMs. And what we mean by textbook, it's not literally textbook. I will explain to you in a minute. But what we mean is roughly, instead of training on web data, random web data, let's train on textbook quality data, textbook material type of data. Okay, and you see the reason why in the previous slide, Llama and Falcon, they would complete this prompt by saying, an AI that kill everybody or that try to understand who was the creator, etc. Whereas ours talk about theory of mind. It's because those guys, they trained on the web, which contains fan fiction, bad fan fictions about AI, whereas we trained on textbook style data, which includes theory of mind type of textbook. So instead of trying to connect the prompt to some kind of sci-fi stories and bad sci-fi stories at that, our model will try to connect it to more academic type of material. Okay, so it really completely changes the feel that you get. And to explain in a little bit more detail how we did this, I won't explain it to you on Phi 1.5 because it's more complicated, but I will explain it to you on Phi 1. And Phi 1, remember, it's our first attempt, which was specifically for coding. All right, so let's go back to what do people did before to train an LLM for code? Well, what they would do is, again, I would go on the web and they would try to collect a data set as big as possible. And there is a very nice data set out there, which is called the stack, of 3 terabytes of data. Okay, so 3 terabytes of data, we're talking about, billions and billions, trillions, in fact, like actually 1 trillion token of code data. Okay, this is scraped from GitHub, and there is all the questions around licensing, and they have a specific subset which is under permissive license that everybody can use, and so on and so forth. And here you can see the distribution of all the languages. So what people would do is that they would train an LLM on this data, trying to predict the next word on this data, and there they would have their coding LLM. But let's open a little bit the black box. Let's look at what a typical page of GitHub looks like, okay? Because after all, if your model is going to learn from that, this is what the model is going to read to understand what coding means. And this is what a typical page of GitHub looks like. Okay, a typical piece of code on GitHub, it looks like this. So, you know, as a human being, good luck to make sense of this, to understand anything about this code. It's not, you know, very meaningful. I don't think it teaches you anything interesting. It's probably a piece at the beginning where you introduce a lot of definition because you're working on a big project, etc. It's not learning material. It's not textbook material. On the other hand, you also have a smaller fraction on GitHub, which looks like this. Now that looks much nicer, right? This is a bunch of functions that are self-contained. You see here the person is defining normalization, defining the Euclidean distance, defining the cosine distance. This person is even nice enough to have comments. You know, there is a doc string here that explains this normalization, it performs the L2 norm, etc. Learning from the left, at least as a human being, is going to be much, much, much nicer than learning from the right. And in fact, I would say it's not only learning as a human being, also learning as an LLM. You're going to get a lot more information per token if you look at the left than if you look at the right. So our premise is extraordinarily simple. Why don't we train an LLM only on things that looks like the left? Okay, but there is a question: how do you filter? How do you select for this left? You know, this left piece, I'm saying textbook material, but what does textbook material mean? And this is where GPT-4 comes in. Okay, we have this incredible tool that have just arrived on planet Earth, right? GPT-4, which is unlike anything we have ever seen before, and in fact, we have not yet seen anything that even equates it so far. So we have this amazing tool. Let's use it. GPT-4 can tell the difference between the two documents on the previous slide. It can tell you that the one on the left is of much higher educational value. So why don't we use GPT-4 on the trillion tokens that I told you about, right? That have been scraped from GitHub, and filter for the high educational value document. Well, we could do that, but one reason why we wouldn't do it is because it costs a lot of money. Okay, that would be very, very expensive. Here I tell you, if you just look at a very specific subset of this 1 trillion token made of 26 billion tokens, so we wanted to teach only Python, and of course only use pages that have a permissive license that we can legally train on. This is only 26 billion tokens, so much smaller than the 1 trillion. And if you would use GPT-4 to label all of this high educational value or not, this would cost you $1 million on Azure OpenAI. Okay, and I don't have them, neither, my team. So instead, what we decided to do is extraordinarily simple again. What we did is we just used GPT-4 on a small fraction of this data. And then we trained another classifier to mimic GPT-4 to classify the rest. Now you're talking about, instead of $1 million, you're talking about $10,000. Okay. So what we did is we used GPT-4 and we then trained a classifier to mimic it to give a score from 0 to 10 of how good it is in terms of educational value. And we decided to keep the top 20%, okay, which means 6 billion tokens. Okay, the top 20% of 26 billion, it's 6 billion tokens. And then we didn't stop there. We did another thing which turned out to be even more important when we moved to Phi 1.5, which is not only did we filter using GPT-4, but we also created purely synthetic data using GPT. And there, again, it was too costly to use GPT-4, so instead we used GPT 3.5, and we generated another extra 1 billion token of really purely educational content. Literal textbook. We wrote synthetic 1 billion tokens of synthetic textbooks with GPT 3.5. Those textbooks, they look like this. You know, there is some NLP to begin. Let's just define what is a singular matrix, etc. And then there is some little piece of code that explains to you how you compute the determinant, how you determine if a matrix is singular or not. Okay. The resulting data, we call it code textbook. And now, instead of training on the 1 trillion unfiltered data like anybody else, we would only train on these 7 billion tokens. Okay. And let's see what the result looks like. Okay, so this is a bit of a busy table, but we're going to walk through it together. You will see it's very simple. So here you have the date of different models. These are the names of all the models. They are all coding models. So you see, it started with Codex by OpenAI back now 2 years ago, okay, in July 2021. And then, it was pretty slow to take off. So, it took 6 months for Cogen to appear, which is an open source model, in March 2022. Then Google came in with the PaLM model, GPT 3.5 came in, then GPT-4. Then things started to accelerate. You see, now we're in 2023 March. That's when we released the Sparks of AGI paper. And after that, you see April, May, June, like a flurry of work started to try to build those coding LLMs. Here I'm giving you the model size and the data set size in terms of number of tokens. So with Codex, it started reasonable with like one version at 300 million tokens, one version at 12 billion, 12 billion parameters, and 100 billion tokens. But you see that it quickly ballooned. Like again, GPT is 3.5 is 175 billion. If you look at, where is it? If you look at PaLM, PaLM is here, 540 billion parameters. Okay, so these models are huge, and you get to data sets which are in the trillion tokens. Now let's look at their performance. And for their performance, I have two columns, but the only one we're going to look at together is Human Eval, which is this benchmark that OpenAI created. And it's a very challenging benchmark for coding. And you see that their Codex model back 2 years ago was scoring 29% with 12 billion parameters and 100 billion tokens. Now, fast forward to just before we released 5.1, there was another model by Microsoft too, actually, which was 16 billion parameters. So, a little bit bigger than Codex, 1 trillion size of the data set, so 10x what Codex uses. And now we're talking about 50+% on Human Eval, which is fantastic. In fact, it is higher than GPT 3.5, which is at 47%, and GPT-4 is only at 67%. So it tells you how difficult this data set. Now, 5.1, look at these numbers. Look at how tiny it looks compared to the competition. It's only 1 billion parameters, so smaller than everybody else. It's only 7 billion tokens, so like incomparable with any of these other guys, and it scores 50% on Human Eval. And just to show you just very, very quickly in one sentence that it's not overfitted to Human Eval, this is another completely different coding benchmark, MBPP, mostly basic Python programs. And you can see that we even beat Wizard Coder on that one, whereas we decided to pick this one after we built our training data. So this was our coding model. So now very quickly, in just 2 minutes, I told you that after 5.1, we built 5.1.5, which was a common sense reasoning. So this is with a smaller team. So 5.1 was with all of my team, 20 plus people. For 5.1.5, we had a much smaller group. So it was myself, Yon Julie, Ronan Aldan, Ali Del Giorno, Surya Gunasekar, and Yintat Lee. And we worked very hard to create 20 billion tokens, purely synthetic, mostly with GPT 3.5. And we trained only on the synthetic data set. So there was zero web data, no web data at all. Okay. And we also created another version with filtered web, which we call 5.1.5 web. So let me just quickly, show you the benchmark results that we got. So we're not going to be able to read all of them, but very quickly, in blue, this is 5.1.5 and 5.1.5 web in dark blue. All the other ones, the black and the grays, are our competition, including, Vicuna, which is a very popular fine-tune of Llama 2 with 13 billion parameters, so 10x larger. And you can see that all of those black and gray, they are mostly below our blue. Okay, so we are at the very least in terms of common sense reasoning and language understanding and knowledge, at the very least, we're competitive to models 10x bigger. In fact, I think we're better, and it's not necessarily showed by all of those benchmarks. But then when you move to multi-step reasoning, like Human Eval, you have a huge jump compared to all the competition. And BPP, same thing. GSM-8K, it's a grade school mathematics benchmark. The comparison is, there is almost no comparison. The Llama 2 model are really, really bad at mathematics. We are doing just fine. Moreover, and this will be the last point that I make, and then I will conclude, creating LLMs that are trained on synthetic data has an extra benefit, which is that you control much more what the model is going to learn. So you have another knob that you can turn for safety, for biases, for toxicity, for all of those things, you can control it much better because you decide to create the data. So this is a Toxigen benchmark, which is one benchmark testing for the toxicity of LLMs. And you can see that Phi 1.5 and Phi 1.5 Web, they score much, much, much higher than all of these other LLMs. Okay, so let me conclude. I have shown to you two models, Phi 1 and Phi 1.5, which are trained on textbook quality data. And I think it's fair to say that they can give you at least 1,000x gain in terms of, total amount of compute that you need to spend as being calculated by the size of the data set times parameter size. And of course, it's just the beginning for us. We're not gonna stick at 1 billion parameters. We're gonna explore what does 3 billion parameter look like, what does 7 billion parameter look like, and stay tuned later this week at Ignite for some news about that. And that's it. Thank you very much.